Most people worry about asteroids, black holes, or the end of the universe. But the more disturbing question is much closer. What if the planet we trust every second is already changing beneath us? Now, we will explore the weird things happening to Earth right now and why ignoring them may be the biggest mistake we make. Get ready? We begin. 24 hours. That is the deal. Every single day of your life. That number has been the foundation of everything. Your alarm goes off. You have 24 hours. Your calendar is built around it. Your flights are scheduled by it. Your doctor's appointment, your dinner reservation, your work deadlines, all of it runs on the assumption that Earth takes exactly 24 hours to complete one full rotation. We were taught this as children. We never questioned it. Why would we? It has always been true. And the science backs it up. For billions of years, Earth's rotation has been slowing down. Gradually, quietly, relentlessly. The culprit is the moon. Its gravity pulls on Earth's oceans every single day, creating tidal friction, a constant drag on the planet's spin. Scientists have confirmed this through fossil records and ancient coral growth rings. 400 million years ago, a single day on Earth lasted only about 22 hours. The moon has been breaking this planet ever since, shaving tiny fractions of a second off each rotation over deep geological time, slowing down, always slowing down. That has been the story of Earth for longer than complex life has existed. Then, around the year 2016, that story changed. The slowdown stopped. Earth reversed course. The planet began spinning faster, not as a theory, not as a projection, as measured fact. Recorded by the most precise timekeeping instruments ever built, atomic clocks operated by the International Earth Rotation and Reference System Service, the IERS, the global scientific body whose sole job is to track exactly how fast Earth spins, down to fractions of a millisecond. These clocks do not drift. They would not gain or lose a single second across hundreds of millions of years. And what they recorded starting around 2016 was unambiguous. Earth was accelerating. In the year 2020, 28 of the 50 shortest days ever recorded since precision timekeeping began in 1960 all fell within that single year. 28 out of 50. In 6 decades of global measurement, nothing like that clustering had ever appeared. The planet was consistently finishing its rotations faster than the standard 24-hour baseline. Then came July 29th, 2022. On that one day, Earth completed a full rotation 1.59 milliseconds faster than a standard 24-hour day, the shortest day ever recorded in the modern measurement era, 1.59 milliseconds. Blink and you miss it. But at planetary scale, that number carries consequences that reach into every piece of technology you depend on. We will get to that shortly. First, understand what is physically happening. Picture a figure skater mid-spin. She starts with her arms stretched wide, rotating at a slow and controlled pace. Then, she pulls her arms in tight against her body. Instantly, she is spinning so fast, it almost looks impossible. No one pushed her. No extra energy entered the system. She simply moved her mass closer to her axis of rotation, and the laws of physics did the rest. This is conservation of angular momentum, one of the most fundamental principles in all of classical mechanics. Mass moves inward toward the axis. Rotation speeds up. Mass spreads outward. Rotation slows. The total momentum of the system stays constant. Always. That is not optional. That is the law. Earth operates by that exact same law. The planet is the skater, and something is pulling its arms in. The question is, what? Earth is not a simple spinning object you can hold in your hand. It is a layered system of almost incomprehensible complexity. A solid iron inner core, a churning shell of liquid iron surrounding it, a vast rocky mantle above that, ice sheets stacked at both poles, oceans covering 70% of the surface, an entire atmosphere wrapped around everything. Any one of these layers, if it shifts its mass distribution, can change how fast the whole planet spins. And right now, evidence is pointing towards several of them shifting at once. For billions of years, the moon kept one steady hand on the brake. Around 2016, something overpowered it. Something redistributed enough mass, deep enough inside this planet or across its surface, to reverse a trend that had run without interruption since before the dinosaurs walked the Earth. When a planet starts spinning faster, the first thing that breaks is not geography, it is time. And that has already begun to trigger a crisis that most people have never heard of. To understand how scientists know all of this with such certainty, you need to understand the instrument. The IERS does not track Earth's rotation the way you might imagine, not with some mechanical sensor bolted to the ground, not with a gyroscope in a laboratory. They use a technique called Very Long Baseline Interferometry, or VLBI. Here is how it works. Radio telescopes positioned at different points across the planet simultaneously receive radio signals from quasars, the brightest and most distant objects in the known universe, some of them billions of light years away. Because these telescopes are separated by thousands of miles, the same signal arrives at each one at a slightly different time. By measuring that difference down to the nanosecond, scientists can calculate with extraordinary precision exactly how fast Earth rotated during that observation window. The quasars themselves are so far away that they function as fixed reference points, essentially. Permanent anchors in the cosmos against which every tiny wobble and shift in Earth's rotation can be detected. This is not casual science. This is the most precise rotation measurement system human beings have ever built. And what that system has been telling us since around 2016 is consistent, repeatable, and impossible to dismiss as noise. The acceleration trend is real. It is not a random spike in the data. It is not an instrument glitch. Year after year, the VLBI network has confirmed the same finding. Earth is completing its rotations faster than the long-term historical average. The direction reversed, and it has stayed reversed. Now, 2023 and 2024 did show some tapering. The rate of acceleration slowed. A few people latched onto that and said the anomaly was correcting itself. But that interpretation misses the point entirely. Earth in those years was still spinning faster than its long-term historical baseline. The planet had not returned to its old rhythm. It had simply stopped accelerating as sharply. That is not a return to normal. That is settling into a new, faster normal. And scientists at the IERS continue to monitor the trend with close attention. Here is where the stakes become very real. Each millisecond that Earth shaves off a rotation does not disappear into the void. It accumulates across hundreds of rotations, across months and years. Those fractions of a millisecond stack up into a measurable gap between what atomic clocks say the time is and what Earth's actual position in space says the time should be under ordinary circumstances. That gap is managed through a system of periodic adjustments. But the gap has to be managed, because if it is not, the entire global positioning system begins to drift. The GPS constellation, the network of satellites orbiting Earth that tells your phone exactly where you are, that guides commercial aircraft, that synchronizes financial transactions and power grids, operates on timing accurate to the nanosecond. 1 nanosecond. That is 1/billionth of a second. The system uses the precise travel time of signals between satellites and receivers on the ground to calculate position. If the clocks on the ground and the clocks on the satellites diverge by even 1 microsecond, 1/millionth of a second, the positional error that results can reach hundreds of meters, not centimeters. Meters. In aviation, in military navigation, in autonomous systems, that kind of error is not an inconvenience. It is a catastrophe. This means that every time Earth quietly finishes a rotation a little faster than expected, a team of engineers somewhere has to quietly update the parameters that keep the whole system calibrated. They do it invisibly. They do it constantly. You open your Maps app, it tells you to turn left in 300 feet, and you have no idea that somewhere in the background, a correction has already been applied to account for the fact that the planet you are standing on is spinning faster than it was 10 years ago. In other words, Earth is quietly skimming milliseconds off every single day and somewhere. A software engineer is awake at 2 in the morning cleaning up the math. That would be manageable if the trend stayed small. But manageable is not the same as permanent. There is a hard limit to how much adjustment can absorb a continuously accelerating planet. The corrections work when the changes are incremental. They stop working when the changes cross a threshold that the entire architecture of global timekeeping was never designed to handle. But if Earth keeps spinning faster, there will come a point where no small adjustment is enough. Instead, humanity will face a choice with no precedent in the history of the digital age, and it could collapse critical infrastructure around the world in a matter of seconds. Most people have heard of a leap second. It sounds almost quaint. A tiny bureaucratic adjustment to the global clock, something that happens quietly in the background while the rest of the world sleeps. The concept is simple. Earth's rotation is not perfectly consistent. Sometimes the planet spins slightly slower than the atomic clocks that define our official timescale. When that gap accumulates enough, scientists at the IERS add a single second to Coordinated Universal Time, the global standard that every digital system on Earth runs on. 1 second gets inserted, usually at midnight on June 30th or December 31st. The clocks pause for a heartbeat, then the world moves on. This has happened 27 times since the system was established in 1972. 27 leap seconds added over 5 decades. Each time, the adjustment was made. Each time, the world kept turning. No catastrophe, no headlines, just a quiet correction, invisible to almost everyone, and then back to business as usual. It seemed harmless, routine, even the kind of thing that happens and nobody notices. That assumption is about to be stress tested in a way it never has been before, because Earth is no longer spinning slower than the atomic clocks. It is spinning faster, and that single reversal of direction creates a problem that the entire architecture of global timekeeping was never built to handle. If the gap between atomic time and Earth's actual rotation continues to grow in this new direction, scientists will eventually have to do something that has never been done in the history of modern timekeeping. They will have to subtract a second, not add one. Remove one, a negative leap. Second, 1 moment. The clock reads 23 hours, 59 minutes, 59 seconds. The next moment, instead of ticking forward to 60 seconds before rolling over to midnight, it would skip that second entirely and jump straight to the next day. 1 second, erased from the timeline of every connected system on the planet simultaneously. Here is why that matters more than it sounds. Every server, every satellite, every router, every financial exchange platform, every power grid controller, every air traffic management system runs on time synchronization. They all talk to each other constantly, exchanging data packets stamped with precise timestamps. These systems were engineered with a very specific assumption baked into their foundations. Time only moves forward. It always increases. It never goes backward, and it never skips. The software that runs the global internet, the software that handles trillions of dollars in financial transactions every day, the software managing the power flowing into your home right now, none of it was written to handle a moment where a second simply does not exist. In 2022, Meta, the company that owns Facebook, published an internal engineering report addressing exactly this scenario. Their conclusion was direct and alarming. A negative leap, second, if implemented, could be a devastating event for the internet as a whole. Their engineers described cascading failures across interconnected systems, servers disagreeing about what time it is, data packets arriving before they were officially sent according to system logs, authentication protocols breaking down because security certificates depend on timestamps being sequential and consistent, the kind of failure that does not announce itself with one big explosion, but spreads silently through interconnected systems like a crack through ice until the surface gives way. Think about it this way. Imagine the entire internet as a massive symphony orchestra, thousands of musicians spread across every continent, playing together without ever being in the same room. Every instrument, every server, every satellite is playing from the same sheet of music, locked to the same beat, the same universal tempo set by atomic clocks. The performance works because everyone is synchronized to the same pulse. Then imagine the conductor suddenly signals everyone to skip a beat, just one beat. Gone. Some musicians catch the signal instantly and jump forward. Others miss it by a fraction. Some are playing from slightly delayed scores and have not received the update yet. Within seconds, the orchestra that was producing something coherent is producing noise, instruments clashing, timing broken. The performance falls apart, not because any one musician made a catastrophic error, but because the shared foundation of synchronization collapsed for one single moment. That is what a negative leap second would do to global digital infrastructure. 1 second of disagreement, cascading through systems that were never designed to survive it. The international scientific and technical community has been aware of this problem. In 2023, the IERS and the International Telecommunication Union agreed to suspend all leap second adjustments, positive or negative, until at least 2035. It is a temporary truce, a decision to hold the problem at arm's length, while engineers and policymakers work out a longer-term solution. But the problem has not gone away. Earth is still spinning faster, the gap is still accumulating, and the clock on that temporary truce is running. But this crisis of timekeeping is only the surface symptom. The real question is what beneath the ground is powerful enough to change the rotation speed of an entire planet. The leap second problem is not abstract. It is not theoretical. We already have proof of what happens when global timekeeping stumbles, even slightly, even for just 1 second in the positive direction. In 2012, a standard positive leap second was added to Coordinated Universal Time on June 30th. This was not a surprise. Scientists announced it months in advance. Engineers had time to prepare. And yet, when that single extra second was inserted into the global clock at midnight, systems began failing almost immediately. Reddit went down, LinkedIn crashed, Mozilla experienced widespread outages. Qantas Airlines reported check-in system failures that grounded flights and stranded passengers at airports across Australia. Multiple large-scale web platforms buckled within hours of that 1 second addition, not because of a cyber attack, not because of hardware failure, because software written by some of the most skilled engineers on the planet could not gracefully handle 1 extra second appearing in the timeline. That was a positive leap second. 1 second added, systems were warned. The world still cracked. A negative leap second has never been implemented, not once in the entire history of modern timekeeping. There is no real-world test case. There is no proven playbook. And the technical consensus among engineers who have studied the problem is that removing a second is significantly more dangerous than adding 1. When you add a second, systems can pause and wait. When you remove a second, systems that expected that moment to exist suddenly find themselves ahead of the official clock. Timestamps collide. Event logs record events that happened in a sequence that the official timeline says is impossible. Distributed systems that rely on every node agreeing on what time it is find themselves in conflict. And when distributed systems disagree about time, they do not gracefully negotiate a solution. They crash, they loop, they corrupt data, or they simply stop communicating with each other entirely. Every system you depend on is part of this web. The GPS network synchronizes to coordinated universal time with microsecond precision. High-frequency trading platforms on Wall Street and in Chicago execute transactions in timeframes measured in microseconds, with timestamps so precise that the sequence of trades can be reconstructed to the millionth of a second. A single moment of temporal ambiguity in those systems does not just cause a glitch. It can trigger cascading automated responses as algorithms detect anomalies and begin executing emergency protocols, amplifying the disruption rather than containing it. Smart power grid controllers synchronize their switching operations across vast geographic regions using UTC as a common reference. Air traffic management systems track the position and timing of thousands of aircraft simultaneously, with coordination that depends on every tower, every radar system, and every onboard transponder agreeing on the same timestamp. These are not systems with comfortable margins for error. They were engineered for a world where time is a fixed, universal, forward-moving constant. That assumption is their foundation. And it is the same assumption that Earth's accelerating rotation is quietly undermining, 1 millisecond at a time. The international scientific community recognized this. In 2023, the International Earth Rotation and Reference System Service and the International Telecommunication Union reached a formal agreement. No leap seconds, positive or negative, would be introduced until at least 2035. The decision was widely reported as a resolution. It was not. It was a postponement, a deliberate choice to freeze the problem in place, while engineers, physicists, and policymakers work out what to do when the gap between atomic time and Earth time grows large enough that it can no longer be ignored. The gap is still growing. Earth is still spinning faster than the long-term baseline. The truce has a 12-year clock on it, and the planet is not waiting for the committee to finish its deliberations. Step back and look at the full scale of what is at stake. The global digital economy generates tens of trillions of dollars in value every single year. Every transaction, every data exchange, every automated system that keeps modern civilization running operates on a shared assumption that time is uniform, consistent, and globally synchronized. That assumption is not just a convenience. It is the structural foundation on which the entire edifice is built. Banks do not just use time to log transactions. They use it to prove which transaction came first, to prevent fraud, to settle disputes, to comply with regulatory requirements, remove the reliability of time, and you do not just inconvenience a few software teams. You pull a load-bearing wall out of a building that billions of people are living inside. There is no software patch fast enough to fix a planet. There is no firmware update you can push to a spinning sphere of rock and iron. When the ground beneath the entire digital world begins to move, the only response available is to adapt to the systems and adaptation at that scale. Across the full complexity of interconnected global infrastructure, takes decades, not weeks, but to understand why Earth suddenly changed its rhythm in the first place. We have to go deeper, deeper than any drill has ever reached, down to the molten heart of this planet itself. Open any Earth science textbook, and you will find the same description. At the center of our planet sits a solid ball of iron and nickel, roughly 1,200 kilometers in radius, incredibly dense, extraordinarily hot, hotter, in fact, than the surface of the sun. Surrounding that solid inner core is a shell of liquid iron approximately 2,300 kilometers thick, the outer core, churning and flowing in slow, massive currents driven by heat and the planet's rotation. This is the standard model. Stable, predictable, a planetary engine running at steady state for billions of years beneath our feet, generating the magnetic field that shields all life on Earth from the full force of solar radiation. That is what the textbooks say. That is what most of us learned. And for decades, it was the best working model scientists had. Then the seismic data started telling a different story. In 2023, researchers Yi Yang and Xiao Dongsong at Peking University published a study in the journal Nature Geoscience that sent a significant ripple through the geophysics community. Their analysis of seismic wave data accumulated over decades from earthquakes around the world pointed to something that had not been observed before in the modern era of Earth science. The inner core, that solid iron sphere sitting at the very center of our planet, appeared to have slowed its rotation relative to the surface. And not just slowed, the data suggested it may have reached a point where it is now rotating slightly slower than the rest of the planet above it, a reversal of the behavior observed in the previous decade, when the inner core appeared to be rotating faster than the surface. This is not a minor adjustment to an existing model. This is the existing model being turned on its head for decades. The scientific consensus held that Earth's inner core rotated independently of the layers above it, and that, for much of the late 20th century and early 2000s, it was spinning slightly faster than the surface, a phenomenon called superrotation. The 2023 findings suggest that cycle has reversed. The inner core appears to have decelerated, shifted, and is now in a phase of subrotation relative to Earth's surface. It is the first time evidence of this kind of behavioral change in the inner core has been captured clearly in the modern observational record. To understand why this matters, you need a picture of what Earth actually is beneath your feet. Think of it not as a solid ball, but as a set of nested gyroscopes. A gyroscope inside a gyroscope, inside a gyroscope, inside a gyroscope. The innermost one is the solid iron core. Around it spins the liquid outer core. Around that sits the rocky mantle, and wrapped around all of it is the thin crust you walk on every day. Each of these layers can rotate, and critically, they do not have to rotate at exactly the same speed. They are coupled to each other, connected through friction and electromagnetic interaction, but they are not locked together like a single rigid object. Now think about what happens when the innermost gyroscope changes speed. It does not change in isolation. Because these layers are coupled, a change in the inner core's rotation rate transmits force outward through the liquid outer core and into the mantle and crust above. The mechanism is not simple mechanical friction alone. The liquid iron of the outer core conducts electricity and carries magnetic fields. So the coupling between the inner core and the layers above it involves complex electromagnetic interactions as well as fluid dynamics. But the principle is recognizable from everyday physics. It is the same principle that makes a gear train work. When the gear at the center changes speed, the force propagates outward through every connected gear in the system. Apply that to Earth. If the solid inner core has slowed its rotation relative to the surface, conservation of angular momentum requires that the momentum it is no longer carrying must go somewhere. The total angular momentum of the system does not simply vanish, it redistributes. And one plausible consequence of that redistribution, supported by the broader pattern of data we have been examining, is that the outer layers of the planet, including the surface you are standing on right now, could respond by spinning slightly faster. The inner gyroscope slows. The outer system compensates. The planet accelerates. This is not a confirmed, settled, singular explanation for Earth's changing rotation rate. The science is genuinely complex, and multiple forces are at work simultaneously, as we have already seen. But the timing is striking. The inner core behavioral shift and the surface acceleration trend both appear to have become detectable in roughly the same era. The connection is being actively studied. What makes this discovery genuinely unsettling is not the mechanics alone. It is what it reveals about how little we actually knew about the interior of our own planet until very recently. We have sent probes to the outer edges of the solar system. We have imaged black holes billions of light years away, and yet the center of the world beneath our feet remained, until now, almost entirely beyond our direct knowledge. But this is only one piece of the picture. Because what is happening deep inside the Earth is not only changing the speed of this planet, it is also weakening the invisible shield that protects every living thing on its surface. The liquid iron of Earth's outer core is not sitting still. It never has. It churns. It flows in massive, slow convection currents, driven by heat rising from the solid inner core below and the cooler mantle above. These currents are not random. They are organized by the planet's rotation into structured columns and spiraling flows that wrap around the inner core like an enormous, slowly breathing engine. And as that electrically conducting iron moves through space, it generates something remarkable, a magnetic field. This is the geodynamo, the mechanism by which Earth produces and sustains the invisible shield that deflects solar wind, traps charged particles in the Van Allen belts, and makes life on the surface possible. Without the dynamo running inside the outer core, Earth's magnetic field would collapse within a geological eye blink. Mars lost its dynamo billions of years ago. Look at Mars today, a barren, radiation-blasted surface with an atmosphere stripped to almost nothing. That is what happens to a planet when the engine inside goes quiet. The dynamo depends on order. It depends on those convection currents flowing in patterns that reinforce and sustain the magnetic field, rather than disrupting it. And that order is sensitive to what the inner core is doing. When the solid inner core changes its rotation rate relative to the liquid outer core surrounding it, the effect is not contained. Think of it this way. Imagine a glass of water sitting on a table. Now, place a spinning ball at the center of that glass and change its spin speed. The water around it does not remain undisturbed. The motion of the ball transfers to the fluid through friction and pressure, creating new flow patterns, disrupting the ones that were already there. Scale that image up by a factor of inconceivable magnitude. Replace the glass with a shell of liquid iron 2,300 kilometers thick. Replace the water with electrically conducting molten metal carrying magnetic fields. And replace the spinning ball with a solid iron sphere larger than the moon, and you begin to approach what is happening inside Earth right now. When the inner core's rotation shifts, it disturbs the convection patterns in the outer core. Those disturbed patterns change the structure and strength of the geodynamo. And a changed dynamo means a changed magnetic field. Not immediately, not overnight. These are geological processes operating on timescales of decades, centuries, and millennia. But the changes are measurable, and they are being measured. The challenge is that no instrument can be sent into Earth's core. The pressure at the inner core boundary is approximately 3 million times the atmospheric pressure at sea level. The temperature exceeds 5,000 degrees Celsius. No material we can manufacture survives those conditions. No drill has ever come close. The deepest borehole ever drilled, the Kola Superdeep borehole in Russia, reached approximately 12 kilometers before the project was abandoned. The inner core sits nearly 6,400 kilometers beneath your feet. We have not scratched the surface of reaching it. So how do scientists know what is happening down there? They listen. Every major earthquake sends seismic waves radiating outward through the entire planet in every direction. These waves travel through rock, through mantle, through liquid iron, through solid iron, and out the other side. Different materials transmit seismic waves at different speeds and in different ways. By placing sensitive seismometers at stations distributed across the globe and recording how long it takes waves from the same earthquake to arrive at different locations, scientists can reconstruct the internal structure of the planet with remarkable precision. It is the same principle as a medical CT scan, except instead of an X-ray machine rotating around a patient, scientists are using earthquakes occurring naturally around the planet. And instead of imaging a human body, they are imaging the interior of a world. Decades of this data, accumulated from hundreds of significant seismic events, have allowed researchers to track not just the structure of Earth's interior, but the movement within it. Changes in the travel time of seismic waves passing through the inner core over years and decades reveal shifts in that core's orientation, and rotation rate. This is the foundation of the 2023 findings in Nature Geoscience. Not speculation. Measured wave travel times, compared across decades of recorded earthquakes, showing a systematic change in how the inner core is positioned and moving relative to the surface above. Essentially, we are taking X-rays of an entire planet by waiting for it to shake. And Earth, to its credit, never runs short of opportunities to do exactly that. The picture emerging from all of this data is one of a planet in motion at every level simultaneously. The inner core shifting its rotation, the liquid outer core responding, its convection patterns disturbed, its dynamo output changing, the surface above accelerating. These are not separate phenomena happening to occur at the same time. They are mechanically connected, one system driving another, forces propagating outward from the center of the Earth to the ground beneath your feet. But not everything that is changing lies beneath the surface, above ground. A redistribution of mass on a truly staggering scale is already underway, and it is tilting the very axis that Earth spins around. There is a line that runs through every map you have ever read. It connects the North Pole to the South Pole, passing straight through the center of the Earth. You cannot see it. You cannot touch it. But everything in modern civilization that depends on knowing where anything is depends on that line staying exactly where it is. Earth's rotational axis, the fixed reference point of the entire modern world. Every GPS satellite in orbit was positioned and calibrated against it. Every coordinate on every nautical chart, every surveying benchmark used to build roads and bridges and skyscrapers, every time zone boundary drawn on a globe, all of it was engineered on the assumption that this invisible line through the planet holds still. This is not a casual engineering choice. It is the foundational assumption of modern navigation. The United States Space Force operates a constellation of more than 30 GPS satellites, each in a precisely calculated orbit defined relative to Earth's rotational axis. Russia's GLONASS system, the European Union's Galileo network, China's Beidou constellation, every global positioning system on Earth uses the same foundation. When you ask your phone where you are, the answer it gives you is the result of a calculation that traces back to where Earth's axis points. The coordinate system your device uses was built around that axis. Every position on the surface of the planet is defined by its relationship to it. For most of human history, treating the axis as fixed was a reasonable engineering choice. It does wobble in small, well-understood cycles. Engineers knew about those wobbles and built corrections for them into navigation systems decades ago. Predictable, manageable, within expected parameters. That was the baseline. Then came the data that rewrote the baseline. In 2021, a study published in Geophysical Research Letters, authored by Suxia Liu and colleagues at the Chinese Academy of Sciences, presented findings that forced a fundamental reassessment. Their analysis showed that the melting of the Greenland and Antarctic ice sheets since the 1990s had caused Earth's rotational axis to drift in a measurable, significant, and unprecedented way. The direction of polar drift had shifted approximately 45 degrees of longitude toward the east compared to its earlier trajectory, and the rate of that drift had accelerated by approximately 17 times compared to the average rate observed throughout the 20th century. Not 17%, 17 times. The axis is moving faster and it has changed direction. Approximately 90% of that change is directly attributable to ice loss in Greenland and Antarctica. To make sense of what is physically happening, picture a merry-go-round at a playground. A child standing at the center of the platform barely affects the spin at all. Their mass is close to the axis of rotation, so it contributes very little resistance. Now watch what happens when that child walks toward the outer edge of the platform. As their mass moves away from the center, the spin changes. The platform responds to where the weight is. If the child moves more toward one side than the other, the whole system begins to tilt and drift in the direction of the imbalance. The rotational behavior of the entire platform is governed by where its mass is distributed at any given moment. Greenland and Antarctica are that child. For millions of years, vast quantities of frozen water have sat locked near Earth's two geographic poles, close to the rotational axis, contributing to a mass distribution that kept polar drift within predictable, stable bounds. Then, beginning in the early 1990s and accelerating sharply through the 2000s and into the 2010s, that ice began melting at rates that have no modern geological precedent. Hundreds of billions of tons of water, formerly frozen near the poles, were released into the global ocean every single year, spreading outward toward lower latitudes. Mass that had been concentrated near the axis moved away from it. The balance of the planet shifted, and the rotational axis responded exactly the way physics says it must, tracking the redistribution of mass the way any spinning object tracks a shift in where its weight is concentrated. The satellite measurements confirming this came from NASA's GRACE mission, the Gravity Recovery and Climate Experiment, and its successor, GRACE-FO. These twin satellites mapped Earth's gravitational field continuously by measuring the minute variations in gravity caused by shifting mass across the planet's surface. Where ice was lost, gravitational pull decreased. Where meltwater accumulated in the oceans at lower latitudes, gravitational pull increased. The data is direct, precisely measured, and continuous across more than 2 decades of observation. Mass moved, the axis followed. The correlation is not disputed. The engineering response to this has been ongoing and invisible to the public. The International Earth Rotation and Reference System Service maintains the International Terrestrial Reference Frame, the global coordinate system against which all positioning satellites are calibrated. As the rotational axis continues to move, that reference frame must be updated. Satellite orbital parameters must be recalculated. Ground station coordinates at facilities across the planet must be revised. These corrections happen on a rolling basis, quietly, in the background, so that the navigation system on your phone keeps telling you the correct turn, without any visible sign that the coordinate system it depends on is being continuously patched to account for a planet that is not holding still. This is not just a problem for GPS. When Earth's rotational axis moves, everything we build, assuming its stability, begins to drift from what engineers and scientists originally calculated. The numbers behind the ice loss deserve to be stated plainly, because the scale of what is happening resists easy intuition. According to data from NASA's GRACE and GRACE-FO satellite missions, Greenland lost an average of approximately 280 billion tons of ice per year between 2012 and 2023. Antarctica lost approximately 150 billion tons per year over the same period. Combined, that's more than 430 billion tons of water leaving the polar regions and redistributing into the global ocean every single year. To connect that to something tangible, that volume of water would fill more than 170 million Olympic-sized swimming pools annually, not as a one-time event, not as a temporary spike, as a sustained, ongoing annual transfer that has been running for more than 3 decades and shows no sign of reversal. Every year, another 430 billion tons. Every year, the distribution of mass on this planet shifts a little further from what it was. Now, apply the physics. The principle governing what this does to Earth's rotation is classical mechanics, the same mechanics that explain the figure skater and the merry-go-round. When mass moves closer to a rotational axis, moment of inertia decreases and rotation speeds up. When mass moves farther from the axis, moment of inertia increases and rotation slows. The poles of the Earth sit close to the rotational axis. The equatorial and mid-latitude ocean basins sit far from it. So when ice near the poles melts and that water spreads into the global ocean at lower latitudes, the mass moves outward and away from the axis. By every classical calculation, that redistribution should be slowing Earth down. Moment of inertia increases, rotation decelerates, but Earth is not decelerating. Earth has been accelerating since around 2016. This is the paradox at the center of everything we have been building toward. The largest ongoing surface mass redistribution on this planet is pushing in the direction of deceleration, and yet the planet is unambiguously speeding up. The atomic clocks operated by the International Earth Rotation and Reference System Service do not lie. The measurements from the VLBI network are not ambiguous. Earth is completing its rotations faster than its long-term historical baseline. Even as the melting ice sheets work against that acceleration, something else is overpowering the brake that the ice melt is applying. That something else is almost certainly coming from below. The inner core behavioral shift, documented in the 2023 Nature Geoscience study, provides the most compelling candidate. If the solid inner core has slowed its rotation relative to the surface, the angular momentum it is no longer carrying redistributes through the system. That momentum does not disappear. It pushes outward through the liquid outer core and into the mantle and crust, driving the surface to spin faster. The internal forcing from the core dynamics appears to be currently dominating over the surface-level braking effect of the ice melt redistribution. The net result is acceleration. But both forces are real. Both are ongoing. Both are measurable. And both are contributing to a rotational system operating well outside the parameters of recent geological history. What makes this scientifically significant, beyond the individual findings, is what the combination reveals about the nature of the change. This is not one system responding to one input. This is multiple large-scale systems operating through different physical mechanisms at different depths and scales, all changing simultaneously and interacting with each other in ways that produce a net outcome none of them would produce alone. The inner core contributes angular momentum toward the surface. The ice melt pushes back against acceleration. The atmosphere redistributes momentum seasonally. The deep ocean responds. The axis drifts. The rotation rate shifts. Each force affects the others. None of them can be fully understood in isolation. This complexity is precisely why predicting where this is heading is difficult. Scientists can measure what is happening with impressive precision. They can identify the contributing forces and model their individual effects. But the interactions between those forces, playing out simultaneously across a system as large and layered as an entire planet, create cascading feedbacks that make long-range prediction genuinely hard. The models are improving. The data is accumulating. But honest scientists will tell you that the full picture is still being assembled. What is already assembled is enough to demand attention. The GPS engineering community is managing two separate but connected correction streams simultaneously, one for the drifting rotational axis driven by ice loss, and one for the changing rotation rate driven by internal dynamics. Both streams require continuous, ongoing work. Both are invisible to the public. Both are essential to keeping the navigation and communication infrastructure that runs modern civilization functioning within acceptable parameters. The gap between what the planet is doing and what the systems built on top of it were designed to handle is being actively managed, but it is being managed reactively, not proactively. And the changes driving that gap are not slowing down. It turns out this planet has been quietly solving an extraordinarily complex physics problem without consulting anyone, and the answer it keeps arriving at is making life genuinely complicated for an entire global community of GPS software engineers. But the ice in the inner core are only two of the forces currently at work on this planet's rotation. Above us, in the atmosphere and the deep ocean, forces that are invisible to the naked eye are stirring Earth's spin in ways that scientists have not yet fully decoded. Most of us carry a picture of Earth in our minds that goes something like this: rock below, ocean on top of the rock, air above the ocean. The solid planet is the thing that matters. The water and the sky are just passengers riding along on its surface, responding to whatever the ground beneath them does, never really pushing back. It is an intuitive picture. It feels right. And it is wrong in a way that turns out to matter enormously for everything we have been discussing. The atmosphere of Earth weighs approximately 5,100 trillion tons. That number sounds staggering until you compare it to the mass of the planet itself. Earth weighs approximately 6 million trillion tons. The atmosphere, all of it, every molecule of air from the ground to the edge of space, represents less than 1/1,000,000th of the total mass of the planet. If you painted a tennis ball with a single coat of paint, the paint would be proportionally thicker relative to the ball than Earth's atmosphere is relative to the planet. The ocean is more substantial, but still represents only about 1/50th of 1% of Earth's total mass. By any intuitive standard, these are thin, lightweight shells draped over an enormous rock. The idea that they could meaningfully affect how fast a planet spins seems almost absurd, which is exactly why the data is so striking. Scientists at NASA's Jet Propulsion Laboratory and at the International Earth Rotation and Reference System Service have measured and confirmed something that defies casual intuition. The atmosphere and the ocean are not passive passengers. They are active participants in Earth's rotation. They continuously exchange angular momentum with the solid land beneath them, and those exchanges are large enough to produce measurable changes in how fast the planet spins. This is not a theoretical prediction. It is a directly observed and precisely quantified phenomenon, tracked in real time by the same networks of instruments that monitor every other aspect of Earth's rotation. The mechanism is real and it is continuous. As wind patterns shift, as pressure systems build and dissolve, as massive air masses accelerate in one direction or slow in another, they push against the surface of the planet. The land pushes back. Angular momentum transfers between the atmosphere and the solid Earth in both directions, constantly, in a ceaseless exchange that never stops. The ocean does the same thing through its currents, its tidal flows, and the slow movement of deep water masses that carry enormous quantities of momentum across ocean basins over months and years. Every season, every year, every decade, this exchange is happening, and it leaves a fingerprint in the rotation data. El Niño makes this concrete. During a strong El Niño event, the distribution of warm water across the tropical Pacific Ocean shifts dramatically. Massive volumes of warm water move eastward toward the Americas. That is a redistribution of mass across thousands of miles of ocean surface. The atmosphere responds, shifting its own circulation patterns in response to the changed ocean temperatures. These shifts in the distribution of atmospheric and oceanic mass, happening simultaneously across the entire Pacific Basin, are large enough to produce detectable changes in Earth's rotation rate. Scientists have measured this directly. Strong El Niño years show a corresponding signature in the rotation data. The planet spins slightly differently because the ocean moved. The 2023 and 2024 El Niño event was one of the strongest on record. Its effects on atmospheric and oceanic circulation were global in scope. The jet stream, the powerful river of wind that flows through the upper atmosphere, roughly 6 to 9 miles above the surface, and governs weather patterns across the entire northern hemisphere. Shifted in intensity and position, the jet stream carries an enormous quantity of angular momentum. When it strengthens, weakens, or moves north or south, it changes how that momentum is distributed between the atmosphere and the surface below. Engineers tracking Earth's rotation at the IERS have to account for these atmospheric angular momentum changes explicitly in their calculations. They are not a minor correction. They are a significant input into the overall rotation budget of the planet. Think about it this way. Sit down in an office chair that spins freely. Stretch both arms straight out to your sides. Now spin. Then pull your arms in tight against your chest. Your rotation speeds up instantly. No one pushed you. No extra energy entered the system. You simply moved your own mass closer to your axis of rotation, and the physics responded automatically. Now reverse it. Push your arms back out. You slow down. You can oscillate your rotation of speed just by moving your arms back and forth, over and over. without ever touching the ground. The atmosphere and ocean do exactly this with Earth. Every time a major air mass accelerates in one direction or a large ocean current shifts its position, it is effectively moving the planet's arms in or out. The effect on any single day is tiny, but it is continuous. It is real, and it accumulates. Over months and years, the atmospheric and oceanic contribution to changes in Earth's rotation rate is significant enough that no accurate model of why the planet is spinning faster can ignore it. What makes the current situation unusual is that multiple atmospheric and oceanic drivers are behaving in ways that fall outside historical norms simultaneously. El Niño events are becoming more intense. The jet stream has been showing unusual behavior, including extended periods of unusual meandering that affect how momentum is distributed across hemispheres. The deep ocean circulation systems that move water and momentum across entire ocean basins on timescales of decades are themselves changing. These are not isolated anomalies. They are concurrent shifts in the atmospheric and oceanic systems that have been contributing to Earth's rotation for as long as Earth has had an atmosphere and an ocean. The rotation of this planet is not governed by one simple clock. It is the net result of forces operating from the center of the Earth all the way to the top of the stratosphere, all interacting with each other, all changing simultaneously. The inner core below, the ice sheets above, the ocean currents wrapping around it all, and the atmosphere breathing over everything. Each one a contributor, none of them acting alone, but there is something stranger still happening, something that does not fit neatly into any of the forces we have discussed so far. A wobble in Earth's rotation that has existed for more than 100 years, observed continuously and reliably, suddenly went nearly silent, and nobody can fully explain why. Earth does not spin perfectly. No planet does. The axis around which Earth rotates is not perfectly fixed relative to the planet's crust. It drifts slowly over time, as we have seen from the ice sheet data, but it also wobbles in a much shorter, rhythmic pattern that has been known to science for over a century. This wobble has a name, the Chandler wobble, and for most of the history of modern geophysics, it was as reliable as the seasons. Seth Carlo Chandler, an American astronomer, first identified the phenomenon in 1891. What he discovered was that Earth's geographic pole, the point on the surface where the rotational axis meets the crust, does not stay fixed. It traces a slow, irregular spiral, wandering in a roughly circular path with a radius of several meters at the surface. The full cycle of this wandering takes approximately 433 days to complete, slightly longer than the calendar year. The wobble is small in absolute terms. The pole moves by no more than about 9 meters from its mean position at the surface, but it is measurable, it is consistent, and it has been observed continuously for more than 130 years across observation stations distributed around the world. The physics behind the Chandler wobble is well understood in broad terms. Every rigid body spinning in space will wobble if its mass distribution is not perfectly symmetric around its rotation axis. Earth is not a perfect sphere. It is slightly flattened at the poles and bulges at the equator, and its mass is not perfectly distributed. This imperfection means that when Earth spins, it wobbles in a predictable way. But Earth is not truly rigid either. It is elastic. It flexes. The oceans redistribute their mass in response to the wobble itself, and the atmosphere redistributes in response to seasonal changes. These redistributions from the ocean and atmosphere continuously feed energy back into the wobble, sustaining it against the natural damping forces that would otherwise cause it to die out over decades. The Chandler wobble is, in a real sense, kept alive by the continuous interaction between the solid Earth, the ocean, and the atmosphere. It is a conversation between layers, ongoing for as long as anyone has looked, or it was, between approximately 2017 and 2021. The amplitude of the Chandler wobble dropped dramatically. Scientists at the Sternberg Astronomical Institute in Russia one of the institutions with a long history of precise Earth rotation monitoring, documented the anomaly and published their findings. The wobble did not stop entirely, but its amplitude fell to levels that had not been observed clearly in the entire modern record of measurement going back to the late 19th century. The reliable, metronome-like oscillation that geophysicists had tracked for over 130 years became, for several years, nearly inaudible. The scientific community noticed, papers were written, data from multiple independent observation networks were cross-checked. The finding held. Something had disrupted the mechanism that normally keeps the Chandler wobble sustained at its characteristic amplitude. The exact cause remains under active scientific discussion. No single explanation has emerged as definitive, but researchers examining the problem have pointed toward changes in deep ocean circulation and redistribution of pressure at the ocean floor as the most likely contributing factors. The ocean is the primary sustaining mechanism for the wobble. If something changes in how the deep ocean moves and distributes its mass, the wobble feels it, and this is where the picture becomes genuinely unsettling in a new way. The deep ocean is not static. It is driven by a global system of circulation that moves water slowly around the entire planet on timescales of hundreds to thousands of years. This system is driven primarily by differences in temperature and salinity between water masses, and it has been operating in a relatively stable configuration throughout the entire period of human civilization. But that circulation system is now showing signs of change. The Atlantic meridional overturning circulation, the large-scale current system in the Atlantic that plays a critical role in distributing heat between the tropics and the North Atlantic, has been weakening. Studies using ocean sediment records and direct current measurements have documented this weakening over recent decades. Changes in that circulation alter how water masses are distributed at depth across entire ocean basins. They change the pressure patterns on the ocean floor. They change how the ocean interacts with the spinning solid Earth beneath it. If the deep ocean circulation is changing, the mechanism that sustains the Chandler wobble changes with it. And if the wobble is a signal of how the layers of this planet are communicating with each other, then a wobble going nearly quiet is not a trivial footnote. It is a planet telling you that something about the conversation between its layers has changed. This is the aspect of the Chandler wobble anomaly that geophysicists find most significant. Not the wobble itself in isolation, but what its behavior reveals about the state of the system as a whole. The wobble is maintained by a balance between the solid Earth, the elastic response of the planet's interior, the ocean, and the atmosphere. When that balance shifts enough to suppress the wobble's amplitude to near zero for several years, it is a signal that the balance between those components has moved. Something in the coupling between Earth's layers has changed its behavior. The good news, if it can be called that, is that the Chandler wobble appears to have begun recovering its amplitude after 2021. The conversation between Earth's layers seems to be resuming. But the episode stands as one more data point in a pattern that is becoming harder to dismiss as coincidence. The inner core changing its rotation, the surface spinning faster, the rotational axis drifting at 17 times its historical rate, the Chandler wobble going nearly silent. Each of these is a different instrument in the same orchestra, and they are all playing a different tune than they were playing 30 years ago. The Chandler wobble is the heartbeat of this planet. When it nearly stopped, something fundamental in how Earth's layers interact with each other had shifted. That is not a catastrophe, but it is a signal that the system is reconfiguring itself. And systems in the middle of reconfiguration do not always reconfigure quietly. And if you think the invisible forces deep in the Earth and the near-silent wobble of its axis are already strange enough, look up at the night sky. Because the invisible shield that protects every living thing on this planet has a hole in it, and that hole is growing. There is something protecting you right now that you have never seen, never felt, and almost certainly never thought about before today. It has no color. It has no texture. You cannot touch it, photograph it directly, or perceive it with any of your 5 senses. And yet without it, you would not be here. Nothing on this planet would be here. It is Earth's magnetic field. And it is the reason this planet has an atmosphere thick enough to breathe, oceans deep enough to sustain life, and a surface temperature stable enough to allow complex organisms to exist at all. To understand what the magnetic field does, look at Mars. Mars is roughly half the size of Earth, but it once had a magnetic field, an atmosphere, and almost certainly liquid water on its surface. Billions of years ago, Mars lost its internal dynamo. The liquid iron in its core stopped churning in the organized way that generates a magnetic field. The field collapsed, and without that invisible shield, the solar wind, the constant stream of charged particles blasting outward from the sun at speeds of hundreds of miles per second, began stripping Mars's atmosphere away, particle by particle, over hundreds of millions of years. Today, Mars has an atmosphere less than 1% as dense as Earth's. Its surface is bombarded by radiation that would be lethal to any unprotected human being within minutes. Whatever water it once had is gone or frozen beneath the surface. Mars is not just a cold, dry planet. It is a cautionary tale about what happens when the engine inside a world goes quiet. Earth's engine is still running. The liquid iron in the outer core is still churning. The geodynamo is still generating a magnetic field strong enough to deflect the solar wind around the planet, creating the magnetosphere, the invisible bubble of magnetic influence that extends tens of thousands of miles into space and acts as the first line of defense between the sun's constant bombardment and the surface below. For most of human history, and for all of human civilization, this shield has been doing its job so reliably that we have never had to think about it. It is simply there, silent, invisible, and essential. That is exactly why what is happening to it demands attention. Earth's magnetic field has been weakening, not in the last few years, not as a sudden event. The weakening has been measurable and consistent for at least 150 years, going back to the earliest systematic magnetic field measurements made in the mid-19th century. The rate of weakening, averaged across the global field, is approximately 5% per century. That sounds gradual. And on the timescale of a human life, it is. But on the timescale of a civilization that depends on satellites, electronics, power grids, and high-altitude aviation, a 5% per century decline in planetary magnetic shielding is not a footnote. It is a structural change to the environment in which all of that infrastructure was built and is expected to keep operating. The global weakening is significant, but there is one region where the weakening is not gradual at all. It is dramatic, it is localized, and it is getting worse. It is called the South Atlantic Anomaly, stretching across a vast region of the South Atlantic Ocean, from roughly the coast of South America, eastward toward the southwestern coast of Africa. The South Atlantic Anomaly is a zone where Earth's magnetic field is dramatically weaker than everywhere else on the planet. In this region, the inner boundary of the Van Allen radiation belt, the zone of trapped charged particles that normally sits safely thousands of miles above the surface, dips significantly closer to Earth. The magnetic shielding that keeps that radiation at altitude is simply thinner here, like a worn patch on a coat that no longer keeps out the cold. And through that worn patch, radiation gets through. The European Space Agency has been monitoring the South Atlantic Anomaly with particular precision using its Swarm satellite constellation, a trio of satellites launched in 2013 specifically designed to map Earth's magnetic field with unprecedented detail. The Swarm data has confirmed what ground measurements had been suggesting for decades. The South Atlantic Anomaly is not static. It is expanding, it is deepening, and in recent years, it has shown signs of splitting into two distinct lobes, a development that geophysicists are tracking closely because it may reflect changes in the flow patterns of the liquid iron in the outer core directly beneath this region. The consequences are already visible to the engineers who operate satellites. Any spacecraft passing through the South Atlantic Anomaly encounters significantly elevated levels of radiation compared to the rest of its orbit. High-energy protons penetrate the reduced magnetic shielding and interact with satellite electronics in ways that cause what engineers call single-event upsets. Spontaneous bit flips in computer memory caused by a charged particle striking a transistor. These are not catastrophic failures in most cases, but they require careful management. NASA ESA and the operators of commercial satellite constellations have had to implement specific protocols for instruments and systems aboard satellites as they pass through the anomaly. Some instruments are powered down entirely during passage through the region. Some spacecraft are placed in protected modes. The International Space Station, which orbits at an altitude of roughly 250 miles and passes through the South Atlantic anomaly on a regular basis, routinely receives elevated radiation doses during those transits, a factor that mission planners must account for in managing crew health and hardware longevity. This is not theoretical. It is operational engineering reality happening right now, driven by a gap in Earth's magnetic armor that did not exist in its current form a century ago and is growing larger with each passing decade. The swarm satellite data has also revealed something more subtle and more structurally important than the simple existence of the anomaly. Beneath the South Atlantic anomaly, in the liquid iron outer core of the planet, there appears to be a region of reversed magnetic flux, a patch where the direction of the local magnetic field is pointing opposite to the dominant direction of the global field above it. This reversed flux region acts like a local short circuit in the geodynamo, weakening the field it generates in the area directly above it. And it is this reversed flux patch, buried thousands of miles beneath the South Atlantic, that geophysicists believe is the primary driver of the anomaly at the surface and in the near-space environment above it. In other words, the hole in Earth's magnetic shield is not random. It is not a surface-level phenomenon. It is a direct fingerprint of something happening in the liquid iron that generates the entire field. The South Atlantic anomaly is the face of a disruption in the geodynamo itself, visible from space, growing over decades, and connected mechanically to the same outer core dynamics that are contributing to the changes in Earth's rotation rate we have been tracking throughout this story. The South Atlantic anomaly is not accidental. It is the visible crack on the surface of the magnetic field, reflecting precisely what is happening thousands of kilometers below in the liquid core, and it connects directly to everything we have been building toward in this story. The South Atlantic anomaly is striking on its own terms, but its real significance lies not in what it is, but in what it reveals about where it comes from and what it connects to. Geophysicists studying the anomaly have traced its origin to a specific feature in the outer core of the planet. Beneath the South Atlantic, in the churning liquid iron that generates Earth's magnetic field, there exists what researchers describe as a blob of reversed polarity, a region where the flow of liquid iron is moving in a direction opposite to the dominant circulation around it, generating a local magnetic field that points the wrong way relative to the global field above. This reversed flux blob sits at the boundary between the outer core and the mantle above it, and it acts like a drain in the geodynamo, pulling field lines downward and inward instead of allowing them to flow outward and upward to reinforce the global shield. This is not a feature that has always been there in its current form. Paleomagnetic data, the record of past magnetic field behavior preserved in ancient rocks and ocean floor sediments as they cooled from a molten state, shows that the South Atlantic region has been a zone of recurring magnetic weakness over geological time. But the current anomaly, in its modern intensity and rate of growth, appears to be a product of changes in outer core dynamics that have been developing over the timescale of centuries to decades. The swarm satellite data shows the anomaly expanding and potentially splitting into two lobes, a pattern that some researchers interpret as reflecting the evolution and possible migration of the reversed flux structure in the outer core beneath it. Now step back and hold the full picture together. The inner core has changed its rotation rate relative to the surface, as documented in the 2023 Nature Geoscience study. That change in inner core rotation disturbs the convection patterns in the liquid outer core surrounding it. Disturbed convection patterns in the outer core alter the structure and output of the geodynamo. An altered geodynamo produces a changing magnetic field at the surface and in space. The South Atlantic anomaly is the most visible expression of that altered magnetic field structure. The Chandler wobble, which is sustained by the interaction between the solid Earth, the outer core dynamics, the ocean, and the atmosphere, went nearly silent between 2017 and 2021, signaling a shift in how those layers are coupling. The surface rotation rate has been accelerating since around 2016, driven at least in part by the redistribution of angular momentum from the changing inner core dynamics. The rotational axis has been drifting at 17 times its historical rate, driven by ice mass redistribution that is itself connected to a climate system being altered by the same warming that is changing ocean circulation patterns. These are not separate stories. They share a common thread running through the liquid iron at the center of the planet. The rotation change, the wobble anomaly, and the magnetic field weakening are not three independent phenomena that happen to be occurring simultaneously. They are three different symptoms with overlapping causes, all rooted in the behavior of the outer core and its relationship with the inner core below and the mantle above. Recognizing that connection is one of the most important insights to emerge from the confluence of data collected over the last 2 decades. This brings us to a question that geologists and geophysicists have been wrestling with seriously. Could what we are observing be the early signal of a geomagnetic reversal? The history of Earth's magnetic field, as recorded in ancient rock formations around the world and in the magnetized minerals frozen into the ocean floor as new crust forms at mid-ocean ridges, is a history of repeated reversal. Over the last 450 million years, Earth's magnetic poles have flipped approximately 170 times. North becomes south, south becomes north. The compass needle points the other way. The average interval between reversals, when calculated across the full geological record, is a few 100,000 years, though the actual intervals have varied enormously, from tens of thousands of years to tens of millions. Some periods saw rapid reversals in quick succession. Others saw the field hold stable for extraordinarily long stretches. The last full geomagnetic reversal occurred approximately 780,000 years ago. It is known as the Brunhes-Matuyama reversal, named after the 2 geological epochs it separates. By the rough average of the historical record, we are past the typical interval. The phrase that appears in popular science writing is that we are overdue. Scientists use that word carefully because overdue implies a schedule, and the geomagnetic reversal record does not operate on a schedule. It operates on a chaotic, nonlinear system with no fixed clock. The last reversal might have been 780,000 years ago, but the one before it was only around 100,000 years before that. While some stable periods have lasted more than 30 million years, the statistics tell you that reversals happen. They do not tell you when the next one will arrive. What scientists can say is that the current weakening of the field is consistent with patterns seen in the paleomagnetic record during periods that preceded past reversals, a weakening global field, regional anomalies of reversed polarity appearing in the outer core, the field becoming more complex and less organized in its structure. These are the fingerprints that show up in ancient rocks from periods before past reversals occurred. That does not mean a reversal is imminent. It does not mean one is certain. The field has weakened before and recovered without reversing. The current weakening could be a precursor to a reversal that is still tens of thousands of years away. Or it could be a fluctuation that stabilizes and reverses course. The honest scientific answer is that we do not know, and current models of the geodynamo are not yet capable of predicting the timing of reversals with any reliability. What we do know is what a reversal, if it occurs, would mean for the world as it currently exists. During a reversal, The field does not simply flip overnight from one orientation to the other. The process takes thousands of years. During that transition, the global field weakens significantly before reorganizing in its new orientation. The South Atlantic anomaly, as extensive as it is today, would be a minor preview of the kind of magnetic shielding gaps that would exist globally during a reversal transition. Satellite electronics, which already require protective management when passing through the anomaly today, would face elevated radiation across every orbit. Power grids at higher latitudes, which are already vulnerable to disruption from geomagnetic storms, would face an environment of sustained elevated vulnerability. High-altitude aviation routes would require rerouting. The biological effects on migratory animals that navigate using the magnetic field would be significant and unpredictable. None of this would happen tomorrow. None of it would happen in your lifetime or your children's lifetimes under most scientific assessments of the current rate of change. But the infrastructure of modern civilization was not designed with any of it in mind, because it was designed during a period of unusual magnetic stability that we assumed, without examining the assumption closely, would simply continue indefinitely. Your compass will keep pointing north for thousands of years to come. Probably, at least in theory. In the meantime, trust Google Maps. But here is the most important question of all. Are all of these things we have been examining, the changing core, the melting ice, the shifting atmosphere, the weakening magnetic field, happening independently of one another, or are they resonating together into something far larger than any of them alone? When most people picture a planetary disaster, a very specific image comes to mind. A volcano erupts, an earthquake levels a city, a hurricane makes landfall and tears through a coastline. These are the disasters we have grown up watching on the news, the ones that fill disaster movies, the ones that civil engineers and emergency planners have spent generations preparing for. And critically, they share a common feature. They are discrete, they happen, they cause damage, and then they end. You can draw a box around them. You can say this event started here and finished there. Our entire modern approach to risk is built on that assumption of separateness. A city has a flood plan. A region has an earthquake building code. A coastal community has a hurricane evacuation route. Each hazard gets its own agency, its own protocol, its own insurance category, its own line item in a disaster preparedness budget. We have spent more than a century refining this approach, and it has saved countless lives. But it carries a hidden assumption buried so deep inside it that almost nobody thinks to question it. The assumption is that the major systems of this planet operate independently of one another, that what happens in the ocean stays in the ocean, that what happens in the core stays in the core, that you can isolate a hazard, study it, build a defense against it, and move on to the next one. That assumption has just been quietly dismantled by everything we have spent this story uncovering. What we have been tracing across the inner core, the rotation rate, the melting ice sheets, the jet stream, the Chandler wobble, and the magnetic field is not a list of separate concerns. It is not 7 different chapters in 7 different disaster preparedness manuals. It is one interconnected system, undergoing simultaneous change across nearly every layer it has, with each layer's change mechanically linked to the others. This is the part of the story that deserves to be said plainly and without exaggeration, because the plain version is already remarkable enough. The solid inner core appears to have shifted its rotational behavior relative to the surface, based on seismic evidence published in 2023. That shift in the inner core does not stay contained within the inner core. It propagates outward through the liquid outer core, disturbing the convection currents that generate Earth's magnetic field. A disturbed magnetic field shows up as a growing, deepening anomaly over the South Atlantic, an anomaly that is already forcing engineers to power down sensitive satellite instruments during specific orbital passes. At the same time, angular momentum redistributing from that same inner core shift appears to be contributing to the surface of the planet spinning faster, a trend that has held since around 2016 and forced the international community to confront, for the first time in the history of modern timekeeping, the possibility of a negative leap second. Meanwhile, an entirely separate but parallel process is unfolding above ground. Hundreds of billions of tons of ice are leaving Greenland and Antarctica every year, and that meltwater is redistributing mass across the planet in a way that has pushed Earth's rotational axis to drift at 17 times its 20th century rate. That same warming climate system that is melting the ice sheets is also altering deep ocean circulation patterns. And those altered ocean patterns appear to be connected to the multi-year collapse in the amplitude of the Chandler Wobble, the planetary heartbeat that had ticked along reliably for more than a century before going nearly silent between 2017 and 2021. None of these are coincidences sitting side by side on a timeline. They are forces transmitting energy and momentum between one another, core to mantle, mantle to crust, crust to ocean, ocean to atmosphere, and back again, in a continuous feedback loop that scientists are only now beginning to map with any confidence. This is the central sobering insight that the data forces us to confront. We are not watching several unrelated planetary quirks happen to occur during the same decade. We are watching one planet undergo a coordinated reconfiguration across nearly every major system it has, all at once, in a way that has not been documented anywhere in the modern observational record. The rotation, the core, the ice, the ocean, the atmosphere, and the magnetic field are behaving like instruments in an orchestra that has started playing a new piece of music, and every section is adjusting in response to what every other section is doing. To understand how unusual this is, you have to understand the time frame in which human civilization itself has existed. Every achievement we associate with being human, agriculture, permanent settlements, written language, mathematics, architecture, every empire and nation that has ever existed, the entire arc of science and technology that put satellites in orbit and computers in every pocket, all of it has unfolded within roughly the last 10,000 years. In the 4.5 billion year history of this planet, 10,000 years is not even a rounding error. It is a sliver so thin that if Earth's entire history were compressed into a single calendar year, the whole of human civilization would occupy the final few seconds before midnight on December 31st. And here is the detail that almost nobody stops to consider. Those 10,000 years were not a random sample of what this planet is normally like. They were an exception. Geologists call this period the Holocene, and it represents one of the most climatically and geologically stable stretches in Earth's entire recorded history. Stable sea levels, a relatively steady global climate, a magnetic field that, while slowly weakening, held within a range gentle enough that nobody building a civilization needed to think about it. Predictable seasons, predictable coastlines, predictable enough rotation that nobody needed to ask whether a day would still be 24 hours long. Every single thing humanity built, our cities, our farmland, our legal systems, our shipping routes, our financial markets, our power grids, our satellite networks, was constructed with the unspoken assumption that this unusually calm chapter of Earth's history would simply continue. We never had to question it because, for 10,000 years, we never had a reason to. That assumption is the quiet foundation underneath everything we have discussed in this story so far. It is not written into any law or engineering manual because it never needed to be. It was simply built into the bones of modern civilization, the same way the assumption of a fixed rotational axis was built into the bones of every GPS satellite in orbit. Nobody designed the global financial system to handle a negative leap second because nobody imagined Earth would speed up. Nobody designed satellite shielding for an expanding South Atlantic anomaly because nobody expected the magnetic field to weaken at the rate it has. Nobody designed coastal infrastructure for a rotational axis drifting 17 times faster than the historical average, because nobody anticipated ice sheets vanishing at that scale within a single human lifetime. So here's the question. This part of the story is really asking, is Earth doing anything unprecedented in its own 4.5 billion year history? Almost certainly not. This planet has survived asteroid impacts that wiped out the majority of life on its surface. It has frozen over entirely during multiple ice ages and thawed again. Its magnetic field has flipped roughly 170 times over the last 450 million years without ending life on Earth even once, compared to what this planet has already lived through. A faster rotation rate and a wandering magnetic anomaly are almost gentle by comparison. The problem is not the planet. The problem is the civilization standing on top of it. We are the first generation of humans to build a globally interconnected, satellite-dependent, microsecond synchronized technological society. And we built every piece of it during the one geological moment when the ground felt like it would never move. Earth is not dying. It has never had any intention of dying. It is doing what it has always done across geological time, shifting, reconfiguring, finding new balances between its layers. The real and uncomfortable question is whether the systems we have built, the ones we trust without thinking about them every single day, were built with enough humility to survive a planet that was never actually promising to hold still. Let us bring this down to ground level, away from the abstractions of moment of inertia and geodynamos, and look directly at the systems that would actually feel the consequences if these trends continue to develop the way the data suggests they might. Start with GPS, because it is the system most directly tied to everything we have covered. The global positioning system was built on two foundational assumptions: that Earth's rotational axis holds a fixed, predictable orientation, and that the planet's rotation rate stays within a narrow, well-understood band. Both of those assumptions are now under active strain. The rotational axis is drifting at 17 times its 20th century rate, driven by the redistribution of meltwater from Greenland and Antarctica. The rotation rate itself has been accelerating since around 2016, driven at least in part by changes deep inside the inner core. Right now, engineers at agencies like the International Earth Rotation and Reference System Service manage both of these shifts through continuous, incremental updates to the International Terrestrial Reference Frame, the global coordinate system that every GPS satellite, every smartphone, and every autonomous vehicle ultimately depends on. These updates work. They have worked for years, but they work because the rate of change has stayed within a range that incremental correction can absorb. If the rate of axis drift or rotational acceleration increases beyond what current models anticipate, the entire architecture underlying global satellite navigation would require something far more disruptive than a routine update. It would require a fundamental redesign of how positioning systems handle a planet whose axis and spin are no longer behaving like fixed constants. Now consider the financial system, because this is where the consequences become measured in dollars rather than meters. High-frequency trading platforms? The algorithmic systems that execute a significant share of all stock and bond trades in markets from New York to Chicago to London operate on timestamps precise to the microsecond. The entire legal and regulatory framework around fair trading depends on being able to prove with certainty which trade happened first. That proof depends entirely on synchronized, sequential, never repeating timestamps, a negative leap second, the kind that scientists may eventually be forced to implement if Earth's rotation continues to outpace atomic time, would briefly make sequential timestamps impossible to guarantee across every connected exchange simultaneously. Meta's own 2022 engineering report warned that such an event could be devastating for interconnected digital systems generally, and financial trading platforms are among the most timing-sensitive systems that exist anywhere in the global economy. A momentary collapse in timestamp reliability does not just create a glitch. It can trigger automated risk management systems designed to halt trading the instant something looks anomalous. And when multiple exchanges trigger those safeguards at once, the result is not a contained inconvenience. It is a cascading failure across markets that are more interconnected today than at any point in financial history. Then there is the power grid, the system most people never think about until it stops working. Modern electrical grids, especially in interconnected regions like the eastern and western United States, depend on every generator and substation operating in precise frequency synchronization, typically 60 cycles per second across the American grid. That synchronization is maintained using timing signals distributed via GPS and coordinated universal time. If the timing reference that grid controllers depend on becomes ambiguous, even briefly, the phase relationships between different parts of the grid can fall out of alignment. Grid operators have safety systems designed to detect this kind of desynchronization and isolate affected sections before a problem spreads. But those safety systems were designed around the kinds of disruptions engineers have historically anticipated: equipment failures, severe weather, sudden demand spikes, not a planetary-scale timing event with no prior occurrence to model against. A localized desynchronization that safety systems cannot immediately diagnose can cascade into the kind of regional blackout that takes hours or days to fully restore. And underneath all of these systems sits the basic plumbing of the internet itself. The network time protocol, the system that keeps clocks on servers, routers, and devices around the world synchronized to within milliseconds of each other, is foundational to nearly everything digital. Security certificates that protect online banking, encrypted communication, and e-commerce all depend on timestamps that move forward in strict, unbroken sequence. If a server's clock briefly disagrees with the rest of the network about what time it is, certificates can appear expired before they actually are, or appear to have been issued in the future, both of which can cause authentication systems to reject legitimate connections automatically. This is exactly the kind of failure that brought down major platforms during the relatively minor positive leap second event in 2012, a negative leap. Second, untested and unprecedented, carries a level of risk that the engineers who study it openly describe as more severe and less predictable. Here is the part of this story that deserves to be said honestly, without softening it and without exaggerating it either. Right now, there is no comprehensive contingency plan across the world's software infrastructure for how to handle a negative leap second. The International Earth Rotation and Reference System Service and the International Telecommunication Union bought time in 2023 by agreeing to suspend any leap second adjustments, positive or negative, until at least 2035. But that agreement did not solve the underlying problem. It postponed the decision. Engineers, physicists, and international standards committees are actively debating long-term solutions, ranging from redefining how coordinated universal time itself is structured, to abandoning the leap second system entirely in favor of an approach that allows a larger, less frequent correction. No consensus has been reached, and there is, as of today, no unified global framework for how the rotation changes happening in the core. The ice sheets, the atmosphere, and the magnetic field should be modeled together as a single interacting system, rather than as separate research projects studied by separate scientific communities using separate funding streams. Now hold all of this against the other half of the truth, because both halves matter equally. Earth itself is not in danger. This is not a planet on the brink of catastrophe. Earth has survived 5 mass extinction events that eliminated the majority of species alive at the time. It has endured roughly 170 magnetic pole reversals over the last 450 million years without its core ever stopping. It has frozen over in global ice ages and emerged again, compared to what this planet has already lived through across 4.5 billion years. A faster rotation and an expanding magnetic anomaly are well within the range of what a living, dynamic planet does as a matter of course. The real vulnerability in this story does not belong to Earth. It belongs to the narrow 10,000-year window of unusual calm that human civilization mistook for the planet's permanent default state, and then built every piece of modern technology on top of that mistaken assumption. The good news, and there genuinely is good news here, is that awareness is the first real step toward preparation. Scientists are not ignoring these signals. The IERS continues refining its measurement networks. Engineers across the technology and financial sectors are actively studying alternatives to the leap-second system specifically because of what we have covered in this story. Geophysicists are working to better integrate core dynamics, ice sheet data, and magnetic field measurements into unified models rather than treating them as separate fields. None of this happens overnight, and none of it happens without first recognizing, clearly and honestly, that these systems are connected. So here is where we land, and it is worth saying with a touch of perspective. The good news is that Earth has been spinning for about 4 billion years and shows no sign of stopping anytime soon. The bad news is that it has never once asked for our opinion on the matter, and it is not about to start now. But standing at the edge of everything we have uncovered, the changing rotation, the restless core, the weakening shield, the fragility of a civilization built on borrowed stability, there is one question larger than all the others waiting for us as we bring this story to a close. So this is the real shape of the story. Earth is not a stage standing still beneath us. It never was. It is a living system, breathing through its core, its ice, its oceans, its air, constantly rebalancing itself across timescales too slow for any human eye to catch in the moment. We built our entire civilization inside 10,000 calm years and quietly called that calm normal. It never was normal. It was a gift, a pause, an exception inside a much longer, much wilder story. What is truly remarkable is not that the planet is changing. It always has. What is remarkable is that we are now alive at the exact moment we can finally see it happening. Measured in milliseconds, mapped by satellites, recorded in the rock itself. Science does not have every answer yet. It may never close every gap. That is not failure. That is honesty. The universe never promised stillness. It only promises more to discover. And the ground beneath your feet is still holding secrets older than memory, waiting patiently for someone curious enough to keep asking what comes next.